Hello, math humans. We're going to do 4.5b. Today we're going to be doing more work with U substitution. So today we're going to talk about evaluating integrals that use U substitution. So there's basically two methods. So remember, if I have an integral of f of x dx and I'm evaluating from a to b, then it's going to be f of x evaluated from a to b, right? So I'm going to do f of b minus f of a. So that's what happens when we evaluate a definite integral. So there are two methods if I'm using U substitution. One is substitute U, so whatever your U was, you substitute back into the original integral, or I guess for your solution, and then you're going to evaluate like this. I'm going to do my original integrand limits. Sometimes, and it gets tricky on multiple choice problems on your AP exam, they're going to want you to evaluate from U or with U still in your integral. And if you do that, you have to redo, you have to manage AGE, the integrand limits. And I'm going to do that by evaluating U at A, and I'm going to evaluate U at B. So we'll do an example, and I'll show you what happens. And I'm going to do the same problem both ways, okay? All right, so if I scoot my paper up a little bit, so for our first example, I want to evaluate from 0 to 1 x times x squared plus 1 to the third dx. And we're going to do it in two different ways. I'm going to do it with method 1, and then I'm going to do it again with method 2. And we've done this problem ad nauseum, right? We know that u is going to equal x squared plus 1. du is going to be equal to a 2x dx. So I know that on my original integral, I'm going to introduce a 2 on the inside and a half on the outside. So my integral becomes 1/2, the integral from 0 to 1 of u cubed du. So this is 1/2 u to the 4th over 4 evaluated from 0 to 1, which is going to be 1 over 8. And then I'm going to substitute my original u back in. Here's the x squared plus 1, and then I'm going to evaluate from 0 to 1. And at this point, I'm going to stop because my assumption is you know how to do this. When I do that math, I get 15 over 8. Okay? So now I'm going to show you the difference between method 1 and method 2. So I'm going to do my integration the same way. So I would have chosen the same u, I would have done my du, I would have evaluated, and then I'm going to go from, I'm going to set this up from 0 to 1 of u cubed du, okay? I'm going to go ahead and integrate. Actually, before I do that, the second method redoes your integrand limits. So my u is x squared plus 1, so I'm going to do u of 0, and I get 1. And I'm going to do u of 1, and these are your original integrand limits. And when I do 1 squared plus 1, I get 2. So if I evaluate from u, this is going to become the integral from 1 to 2 of u cubed du. I'll come down here. This is a half, and I get the same u to the 4th over 4, but now I'm evaluating from 1 to 2, so this is 1 over 8 u to the 4th evaluated from 1 to 2. These problems show up on multiple choice problems on your AP exam all the time. I can evaluate my integral using the original integrand limits, but I have to substitute my original u value back in. Or I can evaluate it with the u, but then I have to redo my integrand limits. So I need to redo my integrand limits, and I just do that by evaluating the u at the original integrand limits, and then I can still get the same problem. And when you do this math, you get the same answer, okay? But you'll see some of these problems, if they ask you to evaluate an integral and all of your answers are in terms of u, that means that you have to redo your integrand limits, because that's the expectation if I evaluate the function or evaluate the integral and I leave the u's in that problem, okay? All right, so let's do another conversation kind of along the same way, and we're going to talk about even and odd functions. So if you'll remember back from pre-calc, an even function is symmetric about the y-axis, and an odd function is going to be symmetric about the origin. And these create entertaining situations when you're trying to integrate. So let's look at an even function, okay? If I had maybe the top half of a circle, and that's a circle, so in theory it's symmetric, so you just have to ignore my crappy drawing, I could integrate from a negative a to b of f of x dx, or because this is symmetric, which means that these two areas are the same, I could do, I guess I should write or I could evaluate from a negative a to 0, and I could double it, right? Because if the image is symmetric about the y-axis, then that means this area is equal to this area, so then I could just double it. Okay, so that's actually kind of interesting. Alrighty. Alright, so then let's do an odd function. Odd functions present a different situation. So let's say I have my typical cubic function, and I want to go from a negative a, and then I want to go to this one over here. Maybe this guy is a positive a, so the same value. I could have done that up here too, but I chose to use a's and b's. So from a negative a to a. So this might be a negative 2 to a positive 2. Well, what you'll notice is this has a negative area, and this has a positive area. And if I integrate from a negative a to a of f of x dx, I'm going to get 0. Because the two areas, any area that's below the axis is negative, any area that's above the axis is positive, those two areas are going to negate each other, and then it's going to give you a 0. Okay? So that's just something that's interesting to think about. Sometimes with integration, you have to get a little bit creative where you integrate from and to. All right, let's do a second example. So example number 2. A little thingy's not working with me very much here, so let's scoot our paper up, and it says to solve the differential equation. So I'm going to be given that dy over dx, remember that is your differential, is equal to 10x squared over 1 plus x cubed. Okay? To be able to solve a differential equation, I'm going to cross multiply, and so I'm going to get dy is equal to 10x squared over the square root of 1 plus x cubed dx. Okay, this is called a separation of variables. So separation of variables. When you're doing these problems in an FRQ, this often earns you a whole point. Woohoo! That's pretty easy. So then I'm going to show that I integrate both sides. Sometimes that earns you a point as well. Because if I integrate dy, I'm going to get y. And now I have some math to do over here. So I'm going to have some U substitution to do. I'm going to let my u equal 1 plus x cubed. My du is going to be 3x squared dx. So the 10's a problem child. We're going to move him. So I'm going to start by writing this as 10 times the integral of x squared dx over the square root of 1 plus x cubed. When I did my U substitution, I need to introduce a 3 on the inside, so I divide by 3 on the outside. It's just polite if you move the 10 first. So then this becomes the integral of 10 thirds. The 3x squared dx is du. And so I'm going to have 1 over u to the 1/2 du. I'm going to rewrite this as 10 over 3 integral of u to the negative 1/2 du. Now when I integrate, to go up a power plus 2 over 2, I'm going to get 10 over 3 times u to the 1/2, and then divided by 1/2 plus c. So I get 10 over 3 times 2 over 1 u to the 1/2 plus c. And so I get 20 over 3. I'm going to put in my u, 1 plus x cubed to the 1/2 plus c. And then I'm going to have to report on another page because I ran out of room. So I'm going to get the integral of f of x dx is equal to 20 over 3 times the square root of 1 plus x cubed and then plus c. So it's actually an interesting situation. Remember that, as I bring back how we started, when I solve a differential equation and I show my work of moving the dx to the other side, this is big. And then when I show that I'm going to integrate both sides, this is also big. And these earn you significant points on your exam, so you need to make sure that you take the time to show that individual step. So I believe that that is all I have for today. It is. Lucky dogs. I will see you soon.